Okay, so good
Yes, sir.
noon.
Now session is yours. Sir, you can start.
Oh, okay. Good noon. My name is Mrinmoy Bhattacharjee, and this is my second talk in the summer school on recent trends in speech processing and its application. I'm currently a postdoc at LEAP Lab in Indian Institute of Science. Previously, I was working as a postdoc at IDIAP Research Institute in Switzerland. So in this talk, I'll be talking about the work that I did at IDIAP Research Institute, which is basically uh, targeting the improvement of automatic speech recognition systems for rare word recognition. I'll start by giving a background of automatic speech recognition, what this problem is, and how do we generally go about solving it. So, speech recognition is the task of interpreting human speech. So, the way suppose I'm speaking, speech recognition would be to use a machine to automatically process the speech signal that I'm producing and transcribe that speech signal into a sequence of words that represent the message that I'm conveying through my speech. So in this setup, the input to the system is either speech signal or features computed from the speech signal, and as output we get a text or a sequence of words. That is what basically the purpose of using an automatic speech recognition system is. We have a speech signal and we obtain the transcribed text of the speech signal from the using the system. Now, speech signal, the way I am speaking, you'll notice that I'll take many pauses in between. I'll be silent for some duration. So these silences in the speech signal should not correspond to any text, right? So the text should only correspond to the signal segments where I am actually speaking a word. So to do that, we always have to do a pre-processing, which is known as voice activity detection or VAD, which is sometimes also called speech activity detection or SAD. Once this pre-processing is done, we have we can get segments from the input signal where we have the voiced regions. The other parts, the silence regions, are ignored. Now, the output that you obtain from the system, the text output, it also may be obtained in a very unformatted manner, where it may not have proper punctuations or the stylistic approach characteristics are not provided. This may happen. So, after we transcribe the speech into a sequence of text, we may have to do some post processing also to make it convert it to a presentable format. So this is a very brief overview of the speech recognition system. We'll now see how we uh, train or build the ASR system and how does it work. So I'll be very brief in this particular thing because the main focus of the talk is to describe how the real world recognition is improved in ASR. So this is I'll just be giving a very brief intro into the automatic speech recognition pipeline. But if you have any doubt, please don't hesitate to interrupt and ask your question. So in this figure, which I have obtained from this blog here, by the way, I'd suggest you to go through this blog. This is a very good blog post on the basics of speech recognition using GMM HMM based system, which was the traditional system for a long time. Nowadays, although we have end-to-end systems, but to properly understand the recent trends in speech recognition, you should understand how the traditional systems worked. So I would strongly suggest you to go through this blog post. So in this figure, what it is being shown is this figure here shows the speech signal, the way we see it when we plot it as a one-dimensional signal. In within this signal, now we know speech is non-stationary signal. So we cannot process the whole speech signal at a time. What we normally do is we split the signal into short-term frames, which are typically of 25 to 30 milliseconds long, assuming that in that small duration the signal would still be to some extent it would be stationary. Now from this small frame we now compute the features. So suppose this is the spectrogram representation of this small segment. From this we can compute any standard feature like MFCC, for example, 39 dimensional MFCC with its delta and double delta features. Now I'm assuming that over the course of the summer school, you have been exposed to all the basics of speech processing pipelines. So I'm not going into the details of these feature computations because these are the standard features. But if you still have any doubt, please ask me. So assuming that this is a MFCC feature, we obtain the feature for this small frame and we pass it to the decoding step. Now what is decoding? In ASR terminology, decoding means given a sequence of audio features or speech signal, what is the corresponding text that that is that is most likely to correspond to this given input feature set. This the way to obtain this set of text corresponding to a given set of features is what is known as decoding in ASR terminology. Now, how this decoding is done? It needs various different models. So here comes the need for training different models for the ESR system. What are the different models that we need? First is the acoustic model. What is an acoustic model? This is basically a model which represents the very basic unit of sound present in the given audio signal. Uh, in the ASR literature, this basic sound unit is referred to as phoneme traditionally. Phoneme is something like uh, pa or t or s or sa. These basic sounds, which form a complete word or sentence, are known as phonemes. And the acoustic model is trained to map a sequence of feature vectors, to the corresponding most likely phoneme. Now, how this acoustic model is built? Traditionally, it was built using HMMs or hidden Markov models, which I'm not going into details, but just suffice to know that HMMs can learn the sequence of HMMs were used to learn a sequence of observations to model a particular class, in this case, a phoneme. So the acoustic model has the ability to get the most likely phone or to provide the most likely phone given a set of input feature vectors. Now the next part is called this lexicon. Now what is lexicon? As I've already mentioned, we are transcribing the speech into a sequence of text, and the text contains sequence of words, and each word has a specific spelling. But we don't always pronounce a word exactly how it is spelled. For example, if you see the word smile here, the pronunciation may be something like this. First, we have a s sound, then a sound, then I sound, and it ends with a sound. So this is different from the spelling of this word. So these the units that you see here, these are the phonemes that I was mentioning. So the acoustic model knows which set of features belong to this phoneme, which set of features belong to this phoneme, and so on. And in the lexicon, we know that which word is represented by which set of phonemes. So if you see in the after the acoustic model has given its result, if you see that there is a sequence where we have this set of phonemes together, we will convert this set of phonemes to the word smile. Similarly, for each of the words that we know, now for training the ASR, there may be infinite number of words in the dictionary, but we cannot train the model for all possible words because since it is a database system, whatever words we see in the training data, only those words we will be able to predict. So we have a finite set of words that this particular a trained ASR system can recognize. Those set of words are listed down in this lexicon along with the words and their phoneme sequence. That is the way they are pronounced. So whenever the acoustic model gives us a set of phonemes, we map it with the lexicon and identify which word this sequence of phonemes is representing. And the third or the last part is called the language model. Now, what is a language model? Suppose uh, the after this after the acoustic model gives its prediction, we convert the set of phonemes to the set of words, and we see that the sequence of word comes out to be something like I, there, go. This is not a proper English, but the model suppose predicts that the speech was I there go, but it should be I go there. This is a very basic example. So the language model is used to correct these kinds of errors where the context of the words uh, is modeled based on what it should be based on the language that we are trying to model. So in English, it has a very particular structure of how a sentence is formed. If that structure is not maintained after we get the set of words, then the language model helps us to correct those sequence and give us uh, uh, a more correct or more likely set of words that may represent the given underlying speech signal. So mathematically, it is represented by this formulation where W is the set of words and X is the set of audio features. So the actual task is to give the posterior probability of the word given a sequence of audio features, because initially we only have the audio features. So given the audio features, what is the posterior probability of these audio features belonging to a particular set of words? And we take argmax over the all the possible set of words that we get, and the sequence of words that has the highest probability is selected. But predicting this term is difficult. So using the Bayes theorem, we convert this into a different problem where we first predict, given a particular word, we assume a particular word and see what is the likelihood of the input features to belong to this word. This word, and we do this over all the words that we know in the lexicon. So we'll have a likelihood for all the words. Given word 1, what is the likelihood that the set of features belong to this word? Given word 2, what is this likelihood? So we'll have different likelihoods for that. Along with that, we have the prior probabilities of the words in the dictionary. So not all words are equally likely. Suppose the word the, it might appear more number of times than, for example, a word like tree. So the probability or the prior probability of a particular word depends on how many times it has appeared in the training data. So once we multiply these two values and then take the argmax of the over all the words, we then again get the most likely sequence of words. Now here, this when you convert this posterior probability to this product of likelihood and prior using the Bayes formulation, this term becomes the acoustic model, as I mentioned here. The result obtained from the acoustic model is is replaced here, and the language model is replaced here. So we can train both these models separately and use them for the decoding. Now let's see how, as I was mentioning, what these models look like. So again, the speech signal, we do the basic speech processing, compute the features. Now from these features, the acoustic model is trained. So the acoustic model takes a set of features and maps it to the underlying phone that it corresponds. And for each of the phone, we'll have a model that can give us, given a sequence of features, what is the likelihood of the particular phone. This is what the acoustic model does. Most generally, traditionally, acoustic models were trained using GMM, HMM based models. Now we then have the pronunciation models or the lexicon. This is the same thing, where for a given word we know the sequence of phones that represent the word. The acoustic model will predict the sequence of phones, and once we have the correct sequence of phones, we can replace it with the actual word that the lexicon indicates. Once we have all the sequence of words, we will see if the context of the words in a sequence are correct based on how the language structure is present. That is done by the language model. So here, suppose an example was cat sits on a mat. If it was wrongly predicted as mat sits on a cat, then it would have been wrong. The language model will help us in correcting these things. This is how the formulation is done, as I already explained. Now, the decoding step that I was mentioning. Once we have all these models trained separately, we can go for the decoding. So for decoding, again, for the test signal, we need to compute the features. The features are known as observations. Observations are passed through the acoustic model to get the probabilities of the different phones. Suppose this segment, a particular frame is passed through this model, it will give the probability of all the phones. The phone that is getting the highest probability will be selected. Similarly, for all the corresponding frames, we'll get the highest probability phone. From this, we'll get the phone likelihoods, and using the lexicon and the n-gram language model, we'll give it to the Viterbi decoder. This is a name for the decoding process. And the language model is called n-gram because it basically knows the context of up to n words. Here n indicates the number of word, the context size. It can be 2-word context, 3-word context, 4-word context, or similarly. So the model is trained in a way that every sequence of 3 words are used to obtain the probability of how likely this sequence of 3 words is based on the training data. Now, using all these models, we go for the Viterbi decoder. Viterbi decoder is basically a dynamic programming based approach to find the best path. So we have a sequence of phones, right, from the acoustic model, and the the each for each frame will have different probabilities for each phone. So if it always take the highest probability phone, it might so happen that, because no model is perfect. So if the acoustic model fails for a particular frame and it gives a wrong prediction of a phone, then the whole prediction of the sequence may become erroneous. So in Viterbi decoding, what we try to do is we try to consider top n predictions and try to see which sequence of phones gives the highest likelihood of the underlying speech transcription. Okay, that is how this decoding step works. If we just take the top one, that is generally known as greedy decoding. But if you take more than one possible phone outputs, then it is called a beam search decoding. So these are technicalities of ASR which may not be important here, but in the future slides when I discuss how we improve the rare word recognition, then these concepts would be useful. So basically, beam search decoding is to consider not just the top prediction, but top n predictions. So because it may be possible that the acoustic model can give a wrong output for a particular sequence of frames. To negate that, we will consider uh, a set of top n predictions. The n is a heuristic which can be decided empirically, but assuming that we know how many top predictions need to be considered, we will take all these predictions across the frames and try to find the best sequence of phones. Suppose for the first frame we take the top prediction, for the second frame we take the second top prediction, and for the third frame we again take the top prediction. So or there may be another sequence where in the first frame we take the second top prediction, in the next frame we take the top prediction. So all these combinations of predictions would give us a final uh, total probability or likelihood of the sequence of words. We will see that which sequence of words or characters give us the highest likelihood given the input signal. Then we consider that particular sequence which has the highest likelihood. So in that the highest likelihood sequence during a beam search decoding, not all frames, for all frames we may not be selecting the top prediction. That's what the main idea is. But if it was a greedy decoding, which is a standard term for that, we will always take the top prediction and use that for the decoding. Now let me come to the main thrust of this talk. Uh, at EDIAP, I was working on speech recognition systems for the air traffic communication domain. So, as you know, when the airplanes fly, the pilots were flying the planes, they continuously communicate with the ground staff or the control towers so that they can coordinate their flight plan, speed, height, altitude, everything, so that because there are many planes in the air, so if to avoid any kind of uh, conflict between the paths of the airplanes, the ground staff or the air traffic controllers, they coordinate between all the airplanes in the air to have all of them uh, fly in their own path without ever uh, conflicting their paths with the other. Now, this communication that happens between the pilots and the air traffic controller, this communication is always recorded. So you must have heard about a black box in the airplanes, which keeps recording the communication that happens in the cockpit. Also, it is recorded in the air traffic control room. Now, the the partners with which we were working, they wanted to process this communication to improve their this communication between the pilot and the air traffic controller, which is in short called an ATCO. So the communication between the pilot and the ATCO, to make it more efficient, they wanted to put in a ASR system in between, and this ASR system would try to transcribe the communication, and once the transcription is obtained, the transcription would be used for further understanding of the communication, so that they can use automated tools to improve the like the performance or the services offered to the flights can be enhanced if the communication is better understood, and it can also be automated better. Uh, Before I proceed, if you have any doubt, please feel free to ask me now.
Sure.
Yes.
Hello.
Yes.
Yes, sir. So this WAD is a segment level information, correct?
Uh, s- we yes, it's basically a segment, but what we do is we try to find it per frame, and the frames, the
Combined
contiguous frames that belong to the voice region are clubbed together into a single segment.
supra-segmental feature, this WAD.
Oh, this is not a feature. It's more like you suppose you have the speech signal. If you see here, so you check each of the frames in the signal. Initially, we don't know where there is voice and where there is silence. So we compare based on some threshold or some rule. We check the energy of each frame and decide whether it is a voiced frame or a silenced frame. Once this is done, we'll have a sequence of frames that belong to the voice segment. So that contiguous sequence will fall under one voice segment. Then there might be another a small sequence of frames which belong to the silence segment. So that segment will be called silence. But these segments may be of different lengths. You don't require that the voice segments should be of same length.
Okay, sir.
Once we have this information, we can then only take the voice segments and ignore the silent segments and proceed with the work.
So we are not extracting MFCC from the silent from the unvoiced region. We are not extracting that.
No, no.
Okay. Okay.
Okay. So, as I was mentioning, the whole purpose of this work was to enhance the ATCO pilot communication. So, in this block diagram, you'll see how this whole setup works. So, this ATCO pilot communication signal is recorded. It is passed through the WAD that we discussed. Then we do a classification of basically who is speaking. If it is the ATCO is speaking, we take that segment separately, and if the pilot is speaking, we take it separately because they will be saying different things. One might be asking a question, the other might be answering a question. So to understand it better, we divide it into two channels. Then we go for the ASR system, which is also known as speech to text. This is the expanded version of this. Once we have the text transcription of this signal, we go to another segment which we call as text to concepts. So what it does is the ATCO pilot communication is a very rule based communication. They have a particular structure to the communication. Uh, if I give you an example, uh, they say the airplane name, the airplane has a code name, whichever plane the pilot is flying. Suppose it has a name of Indigo 123, for example. Then he'll start by saying the name of the plane, and then he'll say something like proceed to some place. This means that the ATCO is directing the pilot to take a particular route in the air. So this structure is different from the way we speak in everyday English. So this text to concept basically processes these sequence of words which are very specific to the ATC communication, and tries to extract what are the different parts in this sentence. As I mentioned, there might be a flight identifier in the sentence. So this part will extract that flight identifier. Then there might be a command like to proceed somewhere, or to slow down, or to go up or down. These commands need to be processed separately. So this block basically does this separation of the actual sequence of text, because speech to text just gives you the sequence of words that the speaker is speaking. It will not tell you anything else. So from the sequence of words, this text to concept extracts those important concepts, and these concepts are then used in the way they need to improve the communication, or some kind of service that they are providing. On top of that, There are radars. You must have heard about radars which keep information about every object that is flying in a particular region. The radars also give some, collect some information, some signals. Those signals may also be used to better improve the performance of these systems. So my focus was basically only on the speech to text component. So the speech to text component or the ASR component is this is basically a hybrid ASR system, which was the traditional way of doing it. Here, as I was mentioning, we have a separate acoustic model and a language model, and the scores from both of these are combined to give the actual transcription of the given audio signal. This pipeline I have already discussed, so I'll not go again into this. But this is how the model or the setup was used in this work. Now, what are the challenges in this domain? So, normal ASR on conversational speech, like the way we are speaking now, is it has its own challenges, but it has a very standard structure to it. But the ATC domain communication is very different from the normal English communication. So it has its very specific uh, challenges. What are these? As I mentioned, dictionary is, or the lexicon that I had previously mentioned, it is also known as dictionary. So don't confuse by the words here. It is basically the set of words that the ASA system has seen and can predict given an input signal. We cannot build a ASA system to predict all the words present in the dictionary. So we have to limit it to the words that we see in the training data. So those words are listed in the dictionary or the lexicon. Both are same thing. Now this dictionary can be of very huge sizes, tens of thousands of words in it. But the problem comes because these words in for ATC communication can change over time. Every month, some of the words may be removed and new words may be added. This is why this is done. I'll explain it in the future slides, but this is one of the challenges that is present. So what happens because of this is we cannot. It becomes difficult to scale the ASR system. Suppose there are different airports in the world, and each airport has its own airspace. Now each airspace has its own set of words that it uses. There might be some overlapping words which all airports use, but then there are also very specific airport specific words which may differ from one airport to another. So if we collect data from one airport and use it to build the ASR, we cannot directly port it to a different airport because there would be some new words in that airport which the ASR would have never seen, and it would not be able to recognize those words. So this is a very big challenge in this domain. So as an objective, uh, the measure of this problem, we have seen that a model that we trained on one data set, it failed 60% more times relatively when it was tested on a data of different airspace. So this is a very huge degradation, and this would not be acceptable. And such a system which doesn't work in these ways, it fails to such large extent, would not at all be used by the clients. So the issue here is that there are specific words to each airports which cannot be recognized by the ASA system trained on a different data. Now, a part of these words are known as waypoints. These waypoints are basically which I mentioned that they can be updated every month or they change over across airports. There are many other set of words, but waypoints are a major set of such words which have this problem. And waypoints are basically names, or waypoints represent a latitude longitude pair of a geographic location in the air, for example. On the ground, to go from one place to another, as we use GPS, for example, we know the GPS gives us the routes from one place to another very accurately from across different paths. It also gives us which route has more traffic, which route has less traffic. It also always tries to give you the most shortest possible path from the source to the destination. So this path is on the ground, but airplanes fly in the air, so they cannot follow the path that we use in the GPS to go from one place to another. They have to use a different set of path, and that path should be such that it doesn't overlap between different other planes which are in the air at the same time. So and you can imagine waypoints to be similar to the the milestones that you have on roads. So you see the milestone give you the distance to a particular place from that location. So the milestone basically give you an indication of which direction you are heading and how far one place is from your current location. So waypoints can be imagined to be a milestone in the air, where you represent that as with a latitude longitude pair, and using these waypoints you can navigate using from the source airport to the destination airport via these waypoints, so that your path is completely free and other airplanes can navigate using a different set of waypoints so that they never overlap. Now the waypoints used across airports may be of huge sizes, suppose more than 10,000. And the words that you see here, for example, Dexon, Mopsa, Domux, these are how these waypoints are named. And these are not actual English words, these are artificially created words. That is the main challenge here. If you remember, I mentioned that in the lexicon, we have the each word and the pronunciation sequence of that word, how that word is pronounced. That we can do for actual real English words, which have a very specific set of pronunciation. But for these artificial words, they do not have any particular set of pronunciation. Uh, it is artificially created, but the pronunciation, since it is not an English word, people can pronounce it in different ways. Although the pronunciation may not vary much because they are very small words, but still, these words cannot be deterministically represented by a sequence of phones. That is one thing. The second problem is these waypoints are again very particular to different airspaces. So the waypoint of one airspace does not uh, belong to another airspace, and if we train the model using the waypoints of one airspace, it will definitely fail for a different airspace. And again, as I mentioned, these waypoints are newly created in particular frequency, and the earlier ones retired, and that way the set of words keep changing. So how do we tackle this problem? Because we cannot keep training an ASR for every time a word changes. Now, how these waypoints are even used in the communication? So uh, the waypoint that I was mentioning, suppose it is represented by this set of characters WYK. It will be, this is an example, and this one is pronounced as Viper. And it has another representation which is given as DL455. Now, in the Artco pilot communication, the same waypoint, the waypoint represents only one location in the whole Earth. But when they speak about this waypoint, they may use three different ways of speaking it. The first can be to say only the characters of this representation. Now, why they are saying whiskey, Yankee, kilo? Because this is the standard in this ATC communication, where they have a ICAO phonetic alphabet. They don't say the alphabet directly, WYK, because it is because there might be noises in this channel, and if you just say the letter may get lost or it may be corrupted because of some interference. So they use specific words, very specific predetermined words for each of the character from A to Z. Each of the character letter has a specific word representing it. They don't mean this word literally. It's based if if they say whiskey in the etc communication, it will definitely mean Dillo means K. These words will never come up in any other context. This is a safety mechanism so that even if there is corruption in the signal, character. So this is why this can also say the same in the form of this alphanumeric representation. So here again you will use the ICAO alphabet. So for D it is delta, for L it is lima, and then 455. Or else they say viper. All these three representation mean the same waypoint. If you will detect either this or this or this, and they'll all mean the same thing. Now, where the problem comes, whenever these first two representations are used, not a problem as such for the ASA system, because the ICAO alphabet, because all communication, when they have to say some code or some flight identifier or something, they'll always use ICAO phonetic alphabet. So in the training data, these ICAO alphabets are very frequently present, and the ASR model uh, gets trained very well to identify these words. So whenever these set of uh, uh, what do you call it representations are used in the communication, we don't have an issue with that. We can easily detect this. Issue comes when the third representation is used, which is basically the name of this waypoint, and it is artificially created, as I mentioned. So since it is artificially created, in the training data, we may have never seen this word. So we obviously would not have the lexicon representing this word or the phone sequence. And in that case, the model doesn't recognize this word and it might recognize some other word which is wrong. This is the main problem with these waypoints. And these waypoints are very frequently used in the communication, but a particular waypoint may be very rarely seen in the data. So there, since I mentioned, waypoints are milestones in the air. So there might be thousands of waypoints from the source to the destination. So they might use one particular waypoint, but that would be a different waypoint from the previous one because the flight is moving from one place to another. So, so all the flights in the air would be using waypoints, and at a time there might be many waypoints that are coming in the communication, but a single waypoint may come only once or twice in the whole communication. So this means that this word is so rarely present in the data. Even if we collect the data from that airspace, we will not see this word as many times as we need, and hence this word will always be a very rare word. And since our models are statistical models, the and they work based on the frequency of occurrence of the words, such words would become statistically very insignificant, and the model would find it difficult to predict these words correctly wherever they are. This is a representation of the airspace with different waypoints. If you see, this is a snapshot that the clients have given us. These are different waypoints in the air. The idea is these, when a flight travels, the flight path is determined by these waypoints. If it has to go straight, it will direct to one waypoint. If it has to go to go right, it will take to a different waypoint. This is how the navigation in air is happening. Uh, If you have any doubts, please ask. No doubts? Am I audible?
Yes,
Yes,
sir.
sir.
You're
You
audible.
Okay, okay. Okay, then I'll proceed. So the problem statement is, in this task, we already have an ASR system with us, but the ASR system fails to recognize these waypoints. So our task is to modify the ASR system in a way that these special waypoint words are boosted in a way that whenever they appear in the communication, the ASR system can recognize them with better accuracy. This will help us in improving, like porting the we have an universal ASR system. We can just modify the ASR for a different ASPs and use it directly there without having to train a ASR from scratch. Because if these special words are not recognized well, then the whole communication becomes unusable. As I mentioned, retraining is not an option, so this is the solution that we have to tackle. And another thing that we need is the solution should be such that a non-expert can also do that. So if we give the clients a set of codes or scripts which can modify the existing ASR, they will just need to identify the set of words that they need to recognize better, and if they pass those words to the scripts that we share, the ASR system would be modified internally, and it will become better to recognize those words that they are targeting. This is the main goal of this work. So to do that, we propose three different methods. Uh, First one is OV addition. Here, OV means out of vocabulary words. As I mentioned, these words may be different from different airspaces. So the universal ASR system, which was trained on some data, if it has to be ported to a different ASPs, it might be the case that there are different words in that ASPs which were not present in the training data. So those words would be called out of vocabulary data because they are not there in the original vocabulary. So the first approach would be to use a method where out of vocabulary words are added to the trained ASR system. We are not retraining the ASR system. We are simply modifying it in such a way that new words which are not present in the original vocabulary can be added to it. The second approach is known as lattice rescoring. Now, what is a lattice? If you remember the way when I was describing decoding, uh, where I was mentioning we can do a beam search decoding, where we use multiple top and uh, predictions of the phones and find the best sequence of phones which may or may not be the top in the consecutive frames. So this way, what we'll have is we'll have multiple sequence of words for a given signal, and we choose only the best one from that. These multiple sequence of possible words that can represent the signal are known as hypotheses. This is a terminology of ASR. So when we do beam search decoding, we'll have multiple possible hypotheses which represent which can represent the signal, and out of those possible hypotheses we only select the one that gives us the best likelihood. But we may need all the top possible hypotheses for different processing, like here in this task. So we always store the top n possible hypotheses in a particular data structure. That data structure which stores the top n hypothesis of a ASR decoding for a given test signal, test segment, is known as a lattice. Lattice basically stores the top n hypothesis of the given audio signal. In this lattice rescoring, we uh, do a particular step where this among the top n hypothesis, we find the hypothesis which has the word that we are targeting, and we enhance the probability of that word so that the final selected hypothesis contains the word that we are targeting. And finally, the last approach is G boosting. Here, G is basically representing the language model. As if you remember, language model is a model which knows how the language structure is, and we build n-gram language models for that. That is, we learn contexts of consecutive n words from the data. So in G boosting, we take the trained language model, which is represented by G, and modify it in a way that the the rare words like waypoints here can be better recognized. So some basic definitions. I'll skip this part, but basically, if you see FST, it means finite state transducers, but these are very technical terms. I'll skip this. I'll try to explain them in more basic terms. Just assume that HCLJ means the final. We build a graph using the as if you remember, we have the hybrid system where we have a separate acoustic model and a separate language model, but we have to combine them together, right? So the combined thing in the form of a graph is represented by HCLG. This is a terminology popularized by the very popular ASR toolkit known as CALD, but you just assume this to be a combination of the acoustic and the language model. Now in OV addition, this combined graph is modified so that we can, so the ASR is already trained and we have this combined graph working for a particular airspace. Now to add new words for a different airspace, we take this graph, we don't train anything. We just, this is also a data structure. So we know how this data structure contains data. We go inside the data structure and we add new words to this data structure in a way that next time we decode using this graph, if the target words are present in the signal, the likelihood that those words will be predicted becomes higher. This is how this OV addition works. And every ASR system always has a Ankh representation, which means that if there is a sequence of phones which do not have any representation in the lexicon, then it will repre- it doesn't know which word to replace word. Ankh means unknown. So whenever there is addition, uh, we modify this Ankh representation in a way that whenever it sees a new word which it didn't know earlier, it will, rather than replacing it with Ankh, it will try to replace it with the word that we are targeting. The second method is lattice scoring. As I mentioned, lattices store the top n hypothesis. Now, among this top n, we again select the one which gives the highest likelihood. And by common sense, it can be understood that if the target words are not present in the best hypothesis, obviously those words are not recognized. But if in any one of the other possible hypotheses that are stored in the lattice, if that word is present, then it is possible that if we somehow select that other hypothesis which has the words that we are targeting, then the recognition would improve. So in lattice scoring, we do basically this. We open the lattice and search for the hypothesis which may have the target word that we want to recognize. If any of the other possible hypotheses have that word, we will give it a boost. The score will be given a boost, so that when we again compute the best hypothesis among all these possible one, this time the one containing the target word will get the highest score. This is how this modification is done. And finally, G boosting. In G boosting, what we do is we have the language model, as I mentioned, and it has the context information of the words in form of n grams. N grams can be 3. Gram means number of words, and n means how many words. Gram means words, and n means the number of words. So if it is a 3-gram model, it will always know the sequence of 3 consecutive words. So in G boosting, what we do is we take the trained language model and we try to improve the score of the 3 grams or the n grams that contain the words that we are targeting. So that suppose uh, my name is Mrinmoy. Now suppose my name is not seen by the ASR. So what I'll do is I'll go into the language model and I'll find that trigram where this particular sequence is present. My name is Mrinmoy, and I'll give it a higher score. So whenever a signal comes which the acoustic model gives predicts the phones that represent my name is Mrinmoy, the language model will give it a high score, and the combined score will then help us to recognize the sequence that we are targeting. These are basically engineering methods that are used to modify a already trained model to improve the recognition of a particular set of words that was not being recognized well previously. This is a graphical representation how this is done. This is an example of the ATC communication. So the a sequence may be direct to ballad, where ballad is a very frequently recognized word, but we suppose need to recognize barman. But barman is very rare word and has very low probability. So we'll artificially improve the score of this word so that whenever there is a confusion between ballad and barman, barman also has a high likelihood to be predicted, and whenever the signal has this word barman, it would be recognized with a better likelihood. Now, as I mentioned, acoustic modeling is to be done to obtain the probability of phones. So we use these deep learning models here because the traditional methods of using GMM, HMM are not used now. These deep models can leverage huge amount of data and give much better performance. So two types of acoustic models we have used. One is a TDNN model. CNN basically convolutional neural networks. TDNN is a time delay neural network. So a combination of these different layers is a very standard practice in ASR literature. This is used to train the acoustic model. Another very recent model which is an end-to-end framework is known as an XLSR model, which is based on wave to vec2 model. We might have heard about this wave to vec2, which basically is a model that takes raw speech signal as input, and tries to predict the phones sequence of phones that particular speech segment can represent. It also has initial CNN parts, which are basically the feature extractors, and the feature extracted by the CNN layers are passed to a set of transformer layers. Transformers are the recent uh, models which are very good at learning the temporal context, and in ASR context is very important. So transformers help us learn the context to identify which phone sequence are present, and finally we get the sequence of phones as output from this model. um, we have worked on only monolingual English ASR. Monolingual means the ASR model knows to recognize only one language, that is English. And these are technical details where the loss function used to train the acoustic model is known as lattice-free MMI, or maximum mutual information criterion. This is a standard uh, loss function used in ASR. There are other loss functions like uh, CTC loss, which is known as connectionist temporal loss, and the other is the transducer loss. These are very popular ASR loss functions. We use this lattice-free MMI function, which is because we were using a hybrid setup, and this loss function gave us the best performance. We use GPU, and the features were MFCCI vectors for the CNN TDNN model and raw audio for XLSR, I mentioned already. And the CNN TDNN model was trained using the Kaldi toolkit, whereas the XLSR is a pre-trained model. I forgot to mention that. This is a pre-trained model which has been released by Facebook. We use it to fine tune on our data and then use it to decode on the test data. And we have used the Espresso toolkit that is based on PyTorch and FaceSet. Any questions?
Then
Okay.
I was just trying to ask if we can use transfer learning to leverage knowledge from the high resource languages for our OIV word in low resource languages.
Yes, yes, we can do that, and it is done frequently because for low resource language you don't have the data, and this is basically one form I'm mentioning, not actual transfer learning, but this XLSR model has been trained on around 400,000 hours of speech data. So it has lot of this pre-training has made it robust to lot of other high resource data. And in our case the ATC data is a low resource data because we don't have much data to train models. So we simply fine tune this model so that the recognition performance of the model improves. But the CNN TDN model is trained from scratch because it is a small model.
Oh, okay, sir. But sir, how can we be ensured that the addition of the OIV word respect cultural nuisance and sensitivities? Can we be sure of that?
Can you please repeat your question?
I said, how can we be assured that additions of OIV word respect cultural nuisance and sensitivities? Can we be sure of that?
Uh, you mean that the models should be tuned to a particular cultural aspects?
Yes,
Since
sir. Yes, sir.
well, uh, this is a difficult aspect since these pre-trained models are trained on a lot of data. They tend to smooth out the cultural variations, or they since it is a speech recognition model, it basically it just learns to extract the actual phones that is being said and becoming robust to different types of pronunciation of these words. So even though it is trained on a lot of data, it is still found not to work so well for the low resource data, or uh, even for example English. We have different types of English. US English is different from British English, and English spoken by other non-native English speakers have their own accents. So the ASR models, which are predominantly trained on the native English speakers' data, would fail or would perform poorly when tested with the speech of non-native speakers who have accented speech. So in that case, uh, the only thing could be done is we can fine tune the model with data specific to a particular region who have a consistent accent characteristics, because to build a general model which can recognize the speech of all types of accents is a very difficult task, and it normally doesn't work very smoothly. So to guarantee that the cultural aspects of different speakers can be um, learned by a single model is very difficult. But I think the work is still going on, and big companies like Google and Amazon, Facebook, they're working on these things. So with more data, you can still get a more uh, respectable performance. Like OpenAI's Whisper is a very popular model, and it gives decent performances even in a zero shot setting. But there is still more scope of improvement, and people have found that fine tuning with the in domain data improves significantly. Does this answer your question?
Yes, sir. Yes, sir.
Sorry, sir. I have a question.
Yes, sir.
Can you explain that contraceptive loss in the XLR web-to-wake model?
Yeah, yeah.
This one.
So contrastive loss is a very popular way of training models nowadays, where you don't directly try to compute the loss by finding the error between the prediction and the true label. Rather, what you do is you give it two different examples. One is the example from the true class, and another is example from the negative class. So the contrastive loss is formulated in a way that the 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 similarity between the prediction, the predicted output with the positive class should be similarity will be should be enhanced, and the dissimilarity of the predicted class with the negative class should be enhanced. So basically, we are trying to cluster the prediction so that if the signal belongs to a particular class, it should all be clustered. All the signals that belong to a particular class should be clustered in a particular region in the space, and it should have a good separation from a different examples from a different class. This approach of training models has been shown to work much better than simple, how to call it, the simple loss functions, error-based loss functions. Is it
But
clear?
sir, yes,
Yeah.
sir. But these models, this neural network models require a lot of data. So in case of this that flight language, what is this called? I'm forgetting.
ATC, yeah, ATC communication.
Air traffic control communication. So for that, these models are used, or the conventional HMM, GMM models are used because they do not contain that much of data. That's what.
Exactly. That's what I was mentioning. So earlier, GMM, HMM based models were used, but now we can use these models. As I mentioned, this is a pre-trained model, so it has already seen around 400,000 hours of data. So it is a very good uh, model already, but it only doesn't know, it has not seen the ATC data. So if we just fine tune it for few number of epochs with the small amount of ATC data that we have, it is seen that these models can significantly perform better than the traditional methods with simple fine tuning on small amount of data.
Okay,
Because,
sir.
yeah,
But that ATC data, the phonetic structure is not, it is not it is a pseudo language type of thing, or a artificially made language. So does the transformer is not trained with that language? So by just fine tuning, we can improve the
so the ATC communication is not entirely artificial. I mentioned that the waypoints, the target words that we are trying to improve recognition, those are artificially created. Other than that, it is normally English communication. So,
Oh,
so if you say Indigo 123 proceed right or proceed left, it is basically English. But in that communication, they'll use these waypoints or specific words which are artificial. So these words are very rarely seen. The challenge is the model can recognize the English words or the ICAO alphabet that I mentioned. These are very well recognized. But the problem comes with these artificial words or the words that get updated. So the model after train, since it is already English, only the way the grammatical structure of the communication is different. So only fine tuning on the ATC data makes the system work very well. But the system still fails when it sees these artificial words. That is where this work comes into play.
okay, sir. Thank you.
Okay. We had, as I mentioned, very less amount of data. 195 hours of labeled ATC data was there, that too with augmentation. And we have used threefold speed perturbation to augment the data. And the language model was a 3-gram language model. And the data for system evaluation was provided by the clients with whom we were working. They gave us the critical corner cases data where the system was failing, and we tried to improve and see how the system performed. So this is how the results we obtained. This was published in ICASP this year. So if you see the baseline system performed, this is basically the F1 score of the recognition. In ASR, the ASR metric that is used to represent ASR result is basically word error rate. But in this problem, word error rate is not the target. The target is among all the rare words that we are considering, how many of them are correctly detected after doing the modification. So that we are representing using F1 score. So if you see, OA is basically the overlap addition method that I mentioned. GB is the G boosting method. LR is the lattice rescoring method, and these are the combination of the methods. So G boosting gives us the most important improvement. The pink bars are using the smaller CNN TDNN model, and the green one is with the XLSR model, which is much larger model, and you can see that the large model already gives better performance than the CNN TDNN model. But when we go for perform the biasing boosting methods that I mentioned, we can improve even further. And when we combine G boosting and lattice scoring, we get the best performance. So we have shown that using these post-processing enhancements of the trained model without using any new training data, we can still improve the ASR performance for the rare words that were not seen during the ASR training. So to conclude, basically a larger acoustic model inherently improves the performance, and G boosting is the most effective method among the methods that we have proposed, and the combination of G boosting and lattice scoring gives the best performance. In future, I plan to integrate the OB addition and G boosting, which we could not do in this work, but if we do this, we might get even better performances. Other directions that I can propose to explore for this problem would be to use the the recently popularly used transducer models, which are end-to-end based models, and they have many approaches people with use, like shallow fusion, density ratio based fusion. These are advanced topics. I cannot go into details about that right now. There are other methods which use try based, which are decision trees to improve the recognition based on the first phone, which path to take so that the correct phone sequence can predict it. These are methods which improve for the end-to-end models. And also, if we use more data, if you can obtain more data, we can obviously improve the fine-tuned models even further, and that would also improve the performance. So that will be all. Thank you for your attention. If you have any questions, please ask.
Yes, sir. So for the language modeling, we are using the statistical bigram diagram method.
Yes.
So if we change it with a more advanced end-to-end approach, so will it improve our performance? I mean,
the language model you're mentioning.
yes, yes.
The transducer based models that I mentioned, these are set up where generally they don't use any traditional language model. So the way it is designed is basically it has an encoder which you can it can be seen as an analogy to the acoustic model in the hybrid setup. This encoder gives an output to another setup called predictor. The encoder gives an output, and there is another setup called predictor, which takes the text input, and the outputs from the predictor and the encoder are combined by a joiner to give the final prediction. So this predictor in this model, all of these are trained in end-to-end fashion. So there, in this case, generally standard setup doesn't have a language model, and the predictor can be a different neural network. It can be RNA and LSTM or any other setup. So this predictor is shown to represent an internal language model. So with transducer models, people are getting very encouraging results, and it is the recent uh, uh, direction in which people are exploring significantly. So the hybrid setup that I discussed about is again becoming a old setup, and people are gradually moving away to this end-to-end setups where they don't use any explicit language model, these bigram models. Rather, they use these end-to-end models which have these inherent language models which are shown or which seem to perform much better. But work is still going on, and probably in future we will have these end-to-end setups which don't need any external language model.
The E2E transducer model, does it mean that conventional LLM models like Lara or stuff like that?
It's not an LLM, but people are trying to integrate LLMs also. But it is basically, as I mentioned, it has three components. One is this encoder, one is predictor, and the outputs of these two. The encoder takes the audio signal as input and gives outputs of embedding. Predictor takes the text embeddings, the corresponding text of the signal, and produces the text embedding. And these embeddings are combined by the joiner setup, and it predicts the text, the phone that is represented by that signal. In the For the predictor, people are trying to use different types of models. So the people are trying to integrate LLMs in various forms in this. Also, people have also tried to use external language models with these end-to-end models, and it was seen that even if the model is performing well, external language models, in case of if the language model is trained on the in-domain data, then even an external language model with these end-to-end models also improves performances. So these are all ongoing work, and we'll have to wait and see where it finally converges. Any other questions?
Thank you, sir.
I was thinking of something, sir, like in the context of African languages like this, if somebody can be able to establish like a framework which we involve community in the process of adding and validating the OLV word by contributing to and providing some linguistic insight. Is it possible like this? Can it be possible for someone to build up like a framework that people can be able to validate and some work by contributing?
If I could understand your question, you mean that you want to build a setup, an ASR pipeline
Like,
for
yeah,
African language.
like a framework that people can be contributing like to forms where local community people comes in to validate some word.
Okay.
Is that very good?
The first thing would be, since many African languages, as far as I know, are low resource languages. So the first contribution of local community could be to provide data. So if you can collect data, that is the first step, because these are all data-based approaches. Without data, these models would never work. And as days are progressing, we're moving towards only big data setups. We are gradually leaving behind the traditional setups where we could use less amount of data and build a system. Those were good, but they had an upper limit of performances. It has been shown by multiple research that just by using extra data, the performance of models improves. So the thrust now is to improve, like increase the model size and also the training data. So the bare minimum that one can do is to collect data, annotate it with the help of the community, so that you have some amount of manually transcribed data, which will allow you to take any pre-trained model or pre-trained setup and fine tune it to the language that you're targeting, so that immediately you'll have a very good system which works for that language to some extent. To further improve that model, we'll have to then go into the technical details and see what is the specific characteristic of the language, why the model may be failing for some cases, and then based on those particular analysis, you can then design the new pipeline, which may be better for the specific case of a language. So I think this should be the way one should proceed. Does this answer your question?
Yeah, yes, sir. Yes, sir. I was just considering that the literacy level of the people in the community, that was where that was kind of very scary if that one will work, if there's some advices related to that one.
No, then that's true. Even but people can still give you speech data, right? So even if they cannot read or write, they can speak. So you can ask them to speak something, even if it is in a local, not a standard language, local dialect, but at least they can speak and give you the speech data. And people like you who understand the language, and other volunteers who are like happy to contribute, can be used to annotate those data and verify that the text annotations of the speech data is correct as far as the language is concerned. This is a very humongous task. Data collection and curation is a very, very important task, but it is a very tiring and boring task. So, but even then, you need to do this, because without data, no system would work. So it will be a combination of the local people who will give you speech data, and volunteers who understand the language, who can annotate the data, and a combination of the speech and the annotation will then be used to build the models.
Yeah, thank you, sir. It was very clear now.
Okay, thank you.
Are
So
there any more questions? No, so I think we don't have any more questions. So
okay,
Sarah's gone for a meeting,
okay,
so so he won't be joining. So thank you very much, sir. It was a really wonderful session. And
thank you,
well,
thank you for having me.
yes, sir. So this is the conclusion of our summer school, 2 weeks long summer school.
Mm-hmm.
And
How was the
so,
whole school?
so it was really good, sir. I mean, we have learned so many new things.
Mm-hmm.
I am basically pursuing an NCA. So speech is
Okay,
so new thing for me. So I'm also learning very, very new stuffs.
okay.
And also the participants also, they have also learned so many things. They have asked me so many questions.
Mm-hmm. Yeah, speech
Thank you.
is a very interesting field, and if interested, you could go into it, and it will give you very satisfying uh, experience. Thank you all for attending.
And thank you, sir. Thank you very much, sir.
Okay, thank you. Have a great day.
And you too. Have a great day
Yeah,
too, sir.
yeah.
Thank you, sir.
Thank you so much. See you all. Bye.
So, hello. So this is the
Yeah,
end of our, no,
is there
this is
anything
the,
after this?
no, there's nothing after this. So I'm just concluding the session. It was a 2 weeks long session and we have learned so many things. So
Yeah, yeah.
sir will send a feedback link to the WhatsApp group. Make sure to fill that. And after that, within few days, sir will give the certificates and all the links of the videos and the resources. I mean the PDFs or the the PPTs and the codes will be collected by sir and it will be given to you all. So this is it. So we have done the summer school. Great wishes for the future. And if anyone also want to do something in that work, you can also join and contact sir. So no attendance will be taken here. So after that, you can drop off, and sir will come back and share the feedback form with the WhatsApp with you in the WhatsApp group. Okay then. Bye.
Yes, okay then. Thank you.
Bye bye. Thank you.
Thank you all. Thank you, Bhavani. Thank you all.